Hey, Physics 30s. Okay, so we're going to talk about Rutherford's model of the atom and how that differs from, it doesn't disprove, sorry, I misspoke in the last video. I speak a lot, actually. But it doesn't disprove J.J. Thomson's model. It expands on his model. It shows that part of his model wasn't quite true. Like there are electrons in all models now from this point on. They might just look different or be in different spots. But he at least discovered that these electrons exist. Now, between these two models, between this J.J. Thomson's model and Rutherford's model, which if you notice at the timeline, let's go off here for 2 seconds. Here's the timeline on this. Oh, I don't have a timeline for this. 803, Thomson's model was, find it, there, 1904. So Dalton's model was around for about 100 years, which is great. Okay, so his lasted for quite a long time. So 1903. That's very mysterious. 1904 was J.J. Thomson's model. And then Rutherford's model was about at 1911, started getting questioned, right, of his validity, right? Then along comes Ernest Rutherford of McGill University, which is pretty cool because McGill is in Canada. He is a British or European professor that was brought over to teach in McGill and do some research in McGill. But he did some experiments to prove him incorrect about parts of his model. Not that electrons didn't exist. They all agree electrons exist now. But how does the model interact in certain experiments kind of change the way we have to think about what the models look like. So if I show you this little experiment here. So here you've got the Rutherford scattering. So this is Rutherford. I'm going to click on this one in a bit, but I want to talk about what the plum pudding model would look like in this experiment. So if I put the plum pudding here, I'm going to click that on. So here's the plum pudding model. It's just a fluid, positively charged fluid. You can see on the legend over here with a bunch of, there's no protons and neutrons in here. These are all just electrons in this positively charged fluid. Okay. And what they did is they just shot a bunch of alpha particles at it. And they produce alpha particles. Madame Curie's been around for a while, playing around with radiation all the time. So they just put a radioactive chunk inside of a concrete container. They just poke a hole in it, and then radiation just streams out of it. So they're going to use these. So I'm going to turn this on and shoot a bunch of them. Okay, so what do you notice? Well, the alpha particles just fly straight on through. They might slow down a little bit or speed up because of the interaction with the negative and positive charges. But based on math and how the model works, this plum pudding model works, the alpha particles just fly straight on through. Nothing happens. So you can just do a little trace here. You can see the traces, they're all straight lines. No matter how fast they're going or how slow they're going, they're just going to go straight on through. Okay. So what he saw, though, was quite different. Okay, so if I go back to the home screen, I hit Rutherford's model. Rutherford's model, what he saw was this instead. So this is scales a little bit off here in a little bit, but what he did is shot high energy alpha particles, and I'll just put the traces in there. And he saw this instead. So he saw a lot of the alpha particles travel straight through. You can see a bunch of them. Like they just travel straight on through. But then he also saw these other alpha particles being deflected at high rates in all sorts of different directions. Right, so you can see a lot of them being deflected at high rates. And what they knew about alpha particles, the alpha particles were positively charged. Okay? So if they're positively charged, then an alpha particle, when it gets close to something that's also positively charged, should be deflected by that. But not all the particles are deflected at all. Some of them are just barely deflected or travel straight on through. So he had to come to some conclusion, sorry, to fix this model where not all these alpha particles are deflected. So he came to the conclusion that a majority of the space between the atoms is empty space, and all of the positiveness is being condensed down to this really, really, really small point. In this case, he called it the nucleus. So he condensed all the positive fluid that would be where all of these electrons would be to the outside edge here. And these dotted lines, those are where the electrons would be in his model. So all of that, rather than being filled with this positive fluid, all the positiveness was now condensed down to the middle. And if one of these alpha particles got close enough to it, that repulsive force between the positive of the alpha particle and the positive, this concentrated positive piece of the nucleus, would cause these alpha particles to be deflected. Okay, here's a more one-on-one example here. So you can see these alpha particles now being pushed around by the positiveness of the, but as you're further away over here, you notice that you're not being deflected as much. So that's what he saw from his experiments. So he modified J.J. Thomson's model to what we call the nuclear or the orbital model of the atom, where most of the mass, most of the mass and half the charge, because it's positive and negative, but majority of the mass was inside this tiny little piece in the middle, and all of the positive was there. All the negative electrons, they were floating around all over the place around the outside, right? Because they knew about bonding theory at this point now, where electrons are kind of shared between them, stuff like that. So he knew the electrons had to be around that somewhere, being able to share with other atoms. So they couldn't be trapped within the middle there. Yeah. Let me get back to my page here. So through a bunch of these experiments, doing this a bunch of times, he had to revise the model. This just talks more or less what I was just saying, shooting alpha particles at a really thin piece of gold metal. You can just hammer it down to really, really thin amounts and shot it off, and then detected the alpha particles being deflected in all sorts of different directions around there. This Rutherford thing is what we're looking at here. And it came down to, he just considered that there had to be a very concentrated positive charge to deflect the alpha particles at the magnitude that he was observing, right? If it was all spread out, then the alpha particles wouldn't deflect as much. So he changed the model to be this model here, this nucleus model. He did make a pretty good idea, or a pretty good hypothesis, that the positiveness was actually made up of positive charged particles. The neutrons haven't been discovered yet, but he thought about protons at this point. His nucleus had a bunch of these protons in it. The neutrons were discovered at a later point by a man named Chapman, I believe. We don't really discuss them later on, but we just take for granted that this happened. And we have this new revised model. Usually you see this kind of model when we talk about nuclear explosions and stuff. We have a really, really small nucleus, and then the outside is where all the orbiting electrons are. Now, I probably will, I'll talk about this one here. Yeah, but it's just nice to know, based on a bunch of experiments shooting these alpha particles and how fast the alpha particles are bouncing back and how fast they were shooting the alpha particles. And when they bounce back, you'd be able to determine the actual size of the nucleus. And he got the size of the nucleus to be down to times 10 to the negative 15. So on your formula sheet, that is a femtometer, right? So a femtometer at the very top here, right, times 10 to the negative 15. And he got the atom itself just a little bit larger than that, by 10 to the negative 10, or 10 to the negative 10, sorry, which is 100,000 times larger than what it is. So if you were to draw the atom itself, the atom goes right to the electrons, and nucleus is in the middle. The atom is everything out to the outside edge. If you were to draw a scale of the atom with a radius of 0.5 millimeters, oh, not a radius, sorry. It just be a nucleus of 0.5 meters. What would the radius, if you're drawing of the atom with the radius, what is the radius of your diagram? This is kind of messed up here. So this would be the nucleus. What if I were to draw the nucleus as 0.5 millimeter in size? How big would I have to draw the actual atom itself? Okay, so if I were to draw 0.5 millimeter, there's my nucleus right there. How large would this have to be to go out to the outside edges of this atom? It's 100,000 times larger, right? So if I assume that 0.5 millimeters was the nucleus, I can write this out as a ratio. I could say that 1.7 times 10 to the negative 10 meters is to 7.5 times 10 to the negative 15 meters. And if I know 0.5 millimeters, what is this top number here? So I just do a little cross multiply divide part. Yeah, what am I doing? Okay, 1.7 times 10 to the negative 10 times 0.5 divided by, I'm actually going to change that into meters. 0.5 meters, 0.5 times 10 to the above. Okay, so doing some cross multiply and dividing here, I got the question mark there, the atom size to be 11.3 meters in size. That's quite a big difference. So if this was this, I would have to draw the outside shell of my atom to be 11 meters in radius. So it'll be 22 meters across. It's quite a big difference. So there's a lot of empty space here. And that's what Rutherford discovered. He discovered all this stuff. It's pretty cool. Back in 1911. Yeah, so it's pretty fun, pretty significant. But there's a problem, and we'll deal with that problem in the next video. Okay? And I'll see you then.